Imagine a star so dense it challenges the very limits of physics. Astronomers have found such an object, Pulsar J09520607. This neutron star is the heaviest ever discovered, over twice the mass of our Sun, yet only the size of a city. It spins at a mind-blowing 707 times per second, making it one of the fastest pulsars known. Its story is dramatic. Locked in a deadly dance with a smaller companion, it has siphoned off material for millions of years, growing heavier and spinning faster. This process has earned it the nickname Black Widow Pulsar, after the spider that consumes its mate. Pulsar J09520607 sits on the edge of a cosmic precipice. Any heavier, and it would collapse into a black hole. It's a living example of the boundary between a star and a singularity. This star is a perfect laboratory for testing physics under the most extreme conditions. If gravity wins, the star will crush itself out of existence. For now it remains a spinning, devouring enigma, matter pushed to its breaking point. The universe once again proves stranger than we can imagine. Pulsar J09520607 is a cosmic heavyweight, teetering on the edge of oblivion. The birth of a neutron star begins with the death of a giant at least 8 times the mass of our Sun. For millions of years the star fuses hydrogen-balancing gravity with outward pressure. But when it runs out of fuel, the core fuses heavier elements until it reaches iron, the end of the line. Fusion stops, pressure vanishes, and gravity takes over in a violent collapse. The result, a supernova, one of the universe's most spectacular explosions. The core collapses in less than a second while the outer layers crash inward, then rebound in a cataclysmic blast. The explosion creates a nebula briefly outshining an entire galaxy. At the center remains the crushed core, a neutron star. Here, protons and electrons are squeezed into neutrons, forming matter of unimaginable density. The core, once thousands of kilometers wide, is now a sphere just 20 kilometers across. A neutron star is a stellar ghost, a monument to the violent death of a giant. It's one of the most extreme objects in the universe. To grasp a neutron star's density, imagine crushing the Sun into the size of a city. The result, a solid city-sized atomic nucleus with no empty space. A sugar cube-sized piece would weigh 1 billion tons, more than Mount Everest. Gravity on its surface is 200 billion times stronger than Earth's. Drop an object from a meter above and it would hit the surface at millions of kilometers per hour. A human would be flattened instantly by the crushing force. When first born, a neutron star surface is over 1,000,000 degrees Celsius. Even after millions of years, it glows in X-rays. These are the universe's pressure cookers, hostile, exotic, and extreme. Neutron stars are the ultimate victory of gravity over matter. Not all neutron stars are alike. They're a family of cosmic oddities. Pulsars are rapidly spinning neutron stars with powerful magnetic fields, sweeping beams of radiation like cosmic lighthouses. If their beam sweeps past Earth, we detect a regular pulse. Magnetars are even stranger, with magnetic fields a quadrillion times stronger than Earth's. Their fields can crack the star's crust, unleashing bursts of gamma rays and X-rays. If a dying star's core is massive enough, gravity wins completely, collapsing it into a black hole, a point from which nothing escapes. Neutron stars, pulsars, magnetars, and black holes are all remnants of stellar death, each revealing different extremes of physics. They show us the spectrum of cosmic transformation. From dense cores to cosmic lighthouses to the ultimate void, each tells a story of the universe's power. These objects are the legacy of stars. They are the universe's most extreme survivors. Most stars are born in pairs, locked in a gravitational embrace. When one becomes a pulsar, things get violent. Black Widow pulsars slowly consume their companions, stripping gas into a superheated accretion disk. This stolen material spirals inward, heating up and glowing in X-rays. As it crashes onto the pulsar, it adds mass and spins the star up to incredible speeds. Over millions of years, the companion can be reduced to a dead husk, or nothing at all. The pulsar grows heavier and faster, but there's a limit, the Tolman-Oppenheimer-Volkoff limit. If the pulsar exceeds this mass, gravity wins and it collapses into a black hole. The process is a cosmic tragedy. The pulsar destroys its partner, then itself. Creation and destruction are intertwined in the universe. Pulsar J09520607 is a prime example, pushing the boundary between star and black hole. These systems are laboratories for extreme physics. They show how cosmic cannibalism shapes the fate of stars. In the end, even the devourer can be devoured. The universe is a place of endless transformation. If a pulsar is a lighthouse, a magnetar is a cosmic death ray. Its magnetic field is a quadrillion times stronger than Earth's, enough to tear atoms apart. Get within 1,000 kilometers and the field would rip you to pieces, atom by atom. Even electronics would be wiped from halfway to the moon. The star's crust is under constant stress. When it cracks, it unleashes giant flares. In a split second, a magnetar can release more energy than the sun produces in 100,000 years. In 2004, a flare from SGR 1806-20, 50,000 light-years away, ionized Earth's upper atmosphere. If it were just 10 light-years away, it could destroy our ozone layer. Magnetars are reminders of the universe's violent, unpredictable power. They are true cosmic monsters. Astronomers once thought planets couldn't survive a supernova. But in 1992 they found planets orbiting Pulsar PSR-B 1257+12, the first confirmed exoplanets. These are second-generation worlds formed from supernova debris. Life on such a planet would be harsh, constant radiation, no true day or night, and a deadly environment. Yet their existence forces us to rethink what's possible. Could life adapt to such extremes, deep underground or shielded by thick atmospheres? The universe is more creative than we imagine. Even in the most violent places, new worlds can arise. To understand the universe's grandest structures, we travel back to the cosmic dawn. The first stars were giants, hundreds or thousands of times the sun's mass. The most extreme were quasi-stars, enormous, short-lived behemoths with black holes at their cores. As the black hole fed on the star's gas, it grew rapidly, eventually leaving behind an intermediate mass black hole. These black holes may be the missing link, the seeds from which supermassive black holes grew. Over billions of years they merged and accreted gas, becoming the anchors of galaxies. Quasi-stars with black holes for hearts may have shaped the universe's large-scale structure. They were architects of cosmic history. From their brief lives came the galaxies we see today. Thankfully, these cosmic monsters are far away. But what if a neutron star entered our solar system? Its gravity would shatter the delicate balance, flinging planets from their orbits and scattering the asteroid belt. Earth's orbit would become unstable, possibly sending us into deep space or crashing us into the sun. If it passed close, tidal forces would trigger planet-wide earthquakes, volcanic eruptions, and colossal tsunamis. The planet's crust would crack. Life as we know it would end. A magnetar wouldn't even need to get close. Its magnetic field could strip our atmosphere from millions of kilometers away. A black hole would consume anything that crossed its path. These scenarios highlight the stability and good fortune of our solar system. The universe is wild and untamed, but we live in a rare, peaceful harbor. Our cosmic home is a sanctuary in a stormy universe.